Assalamualaikum, my friends. I am Hendy Rawan. In this session, I will accompany you in a journey of genetic algorithm. The slides are prepared by Mr. Anditya. So let's get started. We will cover three things in this topic. First, we will find out what is a solution, and then we will review meta-heuristic search and what are evolutionary algorithms. Next, we will go deep inside genetic algorithm itself and the concepts: chromosome, fitness, parent selection, crossover and mutation, and survivor selection. Okay, so let's get started with the first concept in genetic algorithm, which is very important, and that is solution. A solution in genetic algorithm is modeled as a string or array. It's usually one-dimensional array, and for this course, that's what we will be using. Solution is also called a chromosome. It is also called an individual. You will need engineering skills to design a solution. And we keep in mind Occam's razor principle. Whenever possible, use a simpler solution, which in genetic algorithm, meaning an array with fewer number of elements and fewer combinations. So let's check out examples of solution design in genetic algorithm. So this is a traveling salesman problem. The problem is starting from an origin. You need to visit all of the other cities exactly once, then go back to the origin city in the shortest possible route. So how do we model genetic algorithm solutions for this problem? Let's see. Because we have n cities, so our solution is an array of n integers from the first city to the last city. And each of the integer value in that array is the visitation order of that city. Okay. So given a solution, which here consists of an array of 5 integers, we can then calculate the distance. Then the genetic algorithm program will need to find a solution that has the shortest distance. Another problem that we can solve with genetic algorithm is mathematical optimization. So given a function of x, where x is a vector, we want to find this x, which gives the lowest function result. So let's see how we model the solution in genetic algorithm. Let's review that our function input is x, a vector, which means it consists of x1 to xn. So our solution is an array of n floating point numbers. So for example, an array of 4 floating point numbers is 1.05, 1.51, 8.70, and 16.12. After that, we can calculate the result of the solution by evaluating the F equation based on the solution numbers. Another problem is knapsack problem. Here, we need to fit many items into a limited container. We want to fit the best items, optimizing the value of the items given limited available space. So we have items from 1 to 100 here. So our solution is an array of 6 integers, and each integer represents the index of the item. Okay. And meaning we can only have or fit 6 items here. Now given a solution, we can then calculate the value and the weight. Last example here is the water jug problem. So we want to find operations so we can fill a jug with specific volume of water. Assuming we have 6 operations, the solution will be an array of numbers, and each array element refers to the operation number. Given a solution, we can calculate whether doing these operations will solve the problem. Now we move on to the second topic, meta-heuristic search. Meta-heuristic is a higher level heuristic. So what meta-heuristic search does is selecting a lower level heuristic algorithm to find a solution. It will sample only a subset of solutions, which means that not all solutions will be evaluated. This is the challenge that meta-heuristic search wants to solve. Even if we are only given the chance to explore a few numbers of solutions, can we find a good enough solution to the problem? Let's take, for example, mathematical optimization, which for simple cases like this can be done by using first derivative. But what if the equation is more complex? Doing first derivative here is really difficult. We can try doing random search. The red dots here. At least one of the dots here will give you better result than the others. But there is no effort to make the result optimal, and most likely they won't even be close to optimal. Simulated annealing is another approach that is semi-stochastic. So it starts randomly or hot, but as it gets cooler, it narrows down to a more stable solution. Simulated annealing can give very good results with an algorithm that is not too complex. Now what happens if we use genetic algorithm? So first, we can generate random solutions for individuals. And then we pick the best one. For the next generation, we perform recombination and mutation. So now we have new individuals that have some similarities with the previous generation. After we do this for several generations, we have individuals that have better and more optimal solutions. As you can see in this case, after 10 generations, the best solution is already pretty good. Why would we need genetic algorithm if we have other approaches? Let's compare it for a traveling salesman problem. First, if we do it by manual thinking, we don't need an algorithm. But when trying to do it by ourselves, we need a total of 11 hours. So how about using software A with Dijkstra? The algorithm runs in 2 hours, very long, but the resulting route is the optimal one, 7 hours, meaning the total time spent is 9 hours. This is an improvement over manual. Now, how about software B, which uses genetic algorithm? Genetic algorithm is quick, so it can finish in only 10 minutes. Although the generated solution is only close to optimal, so with the result of 7 hours and 20 minutes. But that means the total time spent is only 7.5 hours instead of 9 hours when using Dijkstra. With more complex problem, genetic algorithm can show better advantages in speed. So where does genetic algorithm fit in? We can classify optimization algorithms based on whether they are deterministic or probabilistic. Genetic algorithm is a probabilistic algorithm. It is part of evolutionary algorithms, which is part of evolutionary computation. Probabilistic algorithms are also called Monte Carlo algorithms, which is a way of saying they use random sampling. So, what is this evolutionary computation? That is the parent of all evolutionary algorithms, including genetic algorithm. Let's find out. This is the definition of evolutionary computation. In short, it uses the theory of biological evolution and adapts that theory into programs and algorithms that can be run in a computer. While evolutionary computing is for general computing, evolutionary algorithms are for optimization algorithms that uses biology-inspired mechanisms, most likely survival of the fittest. We will be discussing genetic algorithms here, but there are also other evolutionary algorithms. Generally, all evolutionary algorithms have these concepts. A population can be initiated and terminated when individuals don't survive. Parents that can be recombined and mutated, which result in offspring or children that will be chosen which ones will survive based on their fitness. And the survived ones become the population again. And this process repeats again until an acceptable solution is found or the algorithm is stopped. Evolutionary computing can be applied to many problems, such as scheduling, knapsack problem, or packaging, cutting stock problem, design simulation, and so on. We can use evolutionary computing for designing a jet nozzle in an airplane. And after some generations of solutions, we can pick the solution with the best airflow and efficiency. We can use evolutionary computing for designing optical lenses. And after some generations of solutions, we can pick the solution with the best parameters and optical accuracy. We can use swarm intelligence to perform an operation using multiple objects, like drones. Each drone object moves independently, however, they are guided by parameters to achieve certain objectives, such as making a shape and ensuring they don't collide with each other. So far, we have discussed the background of evolutionary computing and evolutionary algorithms. Let's get down into how genetic algorithms actually work. Genetic algorithms are a particular class of evolutionary algorithms that use techniques inspired by evolutionary biology, such as inheritance, mutation, selection, and crossover. 7 properties of genetic algorithms. You must know individual, any possible solution, population, group of all individuals, search space, all possible solutions to the problem, chromosome, blueprint for an individual, fitness, the quality of a solution, recombination, decomposes two distinct solutions, and then randomly mixes the parts to form a novel solution. And mutation, randomly perturbs a candidate solution. Genetic algorithms work like this. It starts by initiating a random population. Now we have a population. We evaluate the fitness of this population. If it is fit enough, or we have approached the limit of generations, then we stop. Otherwise, we continue to the parent selection and then crossover, which generates offspring. We mutate the offspring, and then we select survivors to generate a new population. And then we evaluate the fitness of the new population, and this repeats until we fulfill the fitness threshold or the algorithm is stopped. Now let's explore chromosome, or we can also call it the design for an individual or a solution. Chromosome is the design of how we represent a solution and how to measure its quality. In the traveling salesman problem, the solution is list of visited cities, and we measure the solution quality as the cost to visit all of the cities using the provided list. The lower the cost, the better quality. For the knapsack problem, the solution is list of selected goals. We measure the quality by using two things here. First is the value of selected goods, and second, if it is overweight, that means the solution is of bad quality. For minimizing or maximizing a function, the solution is input variables. The quality is the evaluation result of the function. How we interpret that quality depends on whether we try to minimize or maximize the function. So chromosome is a blueprint set of parameters which defines a proposed solution to the problem. It is represented in a string or array where each element is usually either binary, 0, 1, integer, or real. The evolution usually starts from a population of randomly generated individuals. Here's how a chromosome can be illustrated visually. Each array here is an individual chromosome. Each box or element is called a gene, and a genotype means a subset of genes. Let's take a look at an example for function minimization. The problem is find x1 and x2. That minimizes this function. And the range of x1 and x2 is between -1 and 3 inclusive. There are several choices here to represent an individual. First, we can use an integer value or a real value. Second, we can use binary encoding to represent integer. Third, we can use integer encoding to represent real. And fourth, we can use real encoding to represent real. This is an example if we just use integer value. And the second one uses real value. As you can see, because integer values has no decimal part, the solution parameters may not be sufficient to achieve the end result. We can also use binary encoding. So the binary array here is encoded using an equation here. That means the phenotype or the values that will be used as input to measure the quality of solution will become real numbers as shown in the right. We can also do similar as before, encoding user using integer and then calculating the phenotype using equations. We can also do the same as before using real encoding. There is a reason why to do that. Instead of just using real numbers, the same as phenotypes. The best practice is if we encode the phenotypes into longer genotypes. Genetic algorithm can then give more optimized results. For example, if we need two elements for phenotype X1 and X2, then the chromosome will have two genotypes, and each genotype contains 3 genes with a total of 6 genes. Genetic algorithm will work with 6 genes per chromosome instead of just 2 genes. This usually gives more optimal results. Let's take a look at a different example, the traveling salesman problem. Here, the number of cities is 6, and each city can be visited only once. So the number of genes in the chromosome is 6, meaning there are 6 cities to be visited in order, and the values of each gene here is the city number or index. The solution 152634 means we first visit city number 1, and then city number 5, then city number 2 to 6, and then 3, and then the last city is number 4. Here's another example for knapsack problem. We have 10 items that we can choose, and maximum items that we can put in the bag is 6. Item 0 is just a placeholder for nothing. So an individual solution that contains 2, 0, 0, 7, 0, 3 means that it puts 3 items in the bag. Item 2, item 7, and item 3. Next important concept in genetic algorithm is fitness function. The fitness function is based on an objective function that evaluates a chromosome and by using the values of a chromosome. The fitness function represents the quality of the solution. So the function will return higher values for better solutions. Why is this needed? Because genetic algorithm works using survival of the fittest principle, meaning that each individual solution is measured by using this fitness function. And solutions with the higher fitness will survive, while solutions with the lower fitness will perish. The fitness function needs to fulfill these characteristics. Clearly defined from the objective function, should be sufficiently fast to compute, should generate intuitive results, and the best or worst candidates should have the best or worst score values. These are examples of fitness functions. The simplest fitness function is if we have an objective function h and we want to maximize that. Therefore, fitness function f is equal to h. But for minimizing the objective function, we can use one of these formulas. Let's see some examples. For traveling salesman problem, we can calculate the fitness function by reading 2 genes at a time, or a gene pair, So we evaluate the path between the two cities. And we do that until the last city visited, then going back to the origin city. If there is an edge connection for each pair of cities in the gene pair, then we calculate the cost. Then the fitness function f becomes 1 per h, where h is the total distance of all visited cities. However, if there is any pair of cities that is not connected, then f becomes 0, as the solution is unusable. This one is example fitness function for knapsack problem. This one is for optimizing an objective function. Let's move on to the next concept, and that is parent selection. Parent selection is a process to select individuals as parents to generate new offspring for the next generation. There are several popular and well-studied methods: roulette wheel selection, tournament selection, and roulette wheel via stochastic acceptance. For roulette wheel selection, individuals are given probability of being selected that is directly proportional to their fitness. So we generate a random number, and the higher the fitness, the more range of numbers represented by that solution, giving that solution a higher chance of being selected by the random number generator. This is pseudocode and illustration for roulette wheel selection. So as you can see in the pie chart that we have 4 individuals or chromosomes with different fitness values represented by the portion of the pie. You can also see that in the scale chart below. If we generate a random number, say 0.32, that means it falls here, which means the individual C2 will be picked, even though it has a smaller fitness value. But you can imagine that individuals with higher fitness values has a higher chance to get picked than lower fitness individuals. For stochastic roulette wheel selection, we first select randomly one individual with uniform probability, but then we have acceptance criteria. So we generate another random number, only accept that individual using this probability equation. Otherwise, we reject the individual and repeat to step 1. As you can see here, the lower fitness individuals here has a lower acceptance probability, while the higher fitness individuals have a good acceptance probability or even 1, meaning that it is directly accepted. For tournament selection, we first enter K, the tournament size individuals from the population at random, and then choose the best individual from pool tournament with probability P. We choose the P, and then choose the second best individual, and the probability is P times minus 1 minus P. And then choose the third best individual with probability P times minus 1 minus P squared, and so on. Next concepts are crossover and mutation. Crossover or recombination matches good parent subsolutions to construct better offspring. But we set the probability of crossover, and it's usually 60 to 70%. There are some kinds of crossovers, for example, single point, 2 points, and endpoint crossover. To do a crossover, you need two parents. For single point, you can see here that we select a point randomly, and then we will get two offsprings using crossover of these two parents based on this point here. For 2 points, you do crossover, but using 2 points here. That results in these offsprings to the right. Mutation is a genetic algorithm technique that simulates the effect of errors that happen with low probability during duplication. By a small probability, about 1%, either change a gene by a small amount or replace it with a new value. There are also other kinds of mutation. Next concept is survivor selection. Survivor selection works by generating new individuals to replace the previous generation. There are two techniques, generational replacement and steady state. Generational replacement also uses elitism approach. So the best chromosomes from the previous generation are copied to the next generation. This ensures the solution quality obtained will not decrease from one generation to the next. And then we generate offsprings for the next generation as well. This is how generational replacement works. You can see there is elitism here. We still do crossover and mutation, and the next generation contains both individuals from elitism and also newly generated individuals. For steady state, we generate new individuals directly, and then by using steady state selection, we replace only a few individuals that becomes part of the next generation. This is illustration of steady state. In this case, the offspring replaces the oldest individual in the population. Okay. This is another example of steady state. But the offspring replaces individual with the worst fitness value in the population. This is another variant of steady state. In this case, we select the best individuals from a pair of parents and its offspring to replace one or all the parents. And those are the techniques needed for genetic algorithm. How do we stop genetic algorithm? There are several criteria that you can use. We can limit the number of generations, or we can have a time limit, or we can stop with fitness plateau, meaning if the difference of fitness between generations are so small, we stop. Or use a fitness threshold. It stops if the fitness is better than some predefined value. Or we stop when population and generations have explored many variations. Evolutionary algorithms, such as genetic algorithms, are suitable for problems that are complex, difficult to understand, cannot use conventional methods, or a real-time system that needs to be quick but does not have to be the most optimal. These are problems that can be solved using evolutionary algorithms. For example, traveling salesman problem, shortest path, and knapsack. So, when choosing a searching method, there are a number of factors that we need to consider. The problem space. Some algorithms are good for only smaller problems. The branching factor and depth of solution. If they are too big, it is a sign that you should not use breadth first search or depth first search. Processor and memory usage. Since there are algorithms that use these resources more efficiently. Does the solution have to be optimal? Because if not, we can use a heuristic algorithm. Of course, if you use a heuristic algorithm, you need to make sure that the heuristic function can be formulated. Conclusion. The methods included in the blind search require enormous memory to solve simple problems. With the current speed and limited computer memory, currently blind search is not yet possible to be implemented in the real world. The only blind search method that might be used is iterative deepening search, as it requires very little memory, even though the processing time is very long. Otherwise, search algorithms that are practical for real-world use are heuristic search algorithms. Among the search methods included in the heuristic search, A star is the best option when we can find heuristic function for the problem to be solved. We can choose the A star variation that best fits the problem to be solved and the resources, time and memory we have. When more than one type of heuristic function is found, we can choose the one that is closest to the actual cost. That's it for our topic, genetic algorithm. I hope you enjoy this topic and see you on the next topic.